Now the fourth step is to state the technical conclusion, and we're going to use that critical region to come to our technical conclusion. The technical conclusion is one of two statements: either reject the null hypothesis or do not reject the null hypothesis. And the criteria that we use for which of these two conclusions, technical conclusions, we reach is this. First says we reject the null hypothesis if the test statistic falls into the critical region. And we do not reject the null hypothesis otherwise. So we're simply going to ask ourselves, does the test statistic fall into the critical region? If it does, then we reject the null hypothesis. If the test statistic does not fall in the critical region, then we do not reject the null hypothesis. So in this particular example, our test statistic is z is 2.63. Our critical region is the interval from 1.645 to infinity. And so we see that our test statistic does lie in the critical region. And so we use our first criteria to come to the technical conclusion of reject the null hypothesis. Now, this conclusion is called the technical conclusion because it doesn't mean much of anything to anybody other than the person doing the analysis. And so the last step is to state the final conclusion in non-technical terms. And so to come to our final conclusion, we're going to look at two things. Number one, the technical conclusion, which is either reject or do not reject the null hypothesis. And then we're also going to look at our original claim and ask, does that original claim contain equality? And if it does, then we're going to use one of these two final conclusions. If the original claim does not contain equality, then we're going to use one of these two statements of the final conclusion. Okay? So now by the original claim, we don't mean the null or the alternative hypothesis. We mean the original claim as it was stated in mathematical notation. So in this particular example, our claim was that more than half of students are from out of state. So in mathematical notation, it's the claim that p is greater than 0.5. Now in this particular example, this claim is the same as the alternative hypothesis, but that won't always be the same. And so when we look at the original claim, we don't look at just the null or alternative hypothesis. We go back to the original claim and state it in mathematical notation and ask ourselves, does that claim contain equality? In this case, it doesn't, because it was simply p is greater than 1/2. And so we're going to look at this column here, and our technical conclusion was to reject the null hypothesis. And so our final conclusion is this: the data support the claim. So our sample data appeared to support the claim, and our hypothesis test indicates that the strength of the support was strong enough for us to conclude that the data do indeed support the claim. Now, this interval method is one way of coming to the technical conclusion. Another way of coming to the technical conclusion is called the p-value method. The p-value is going to be a probability, hence the name p-value, and this probability is going to be an area underneath an appropriate density curve. And the density curve that's appropriate is the same density curve that the critical value comes from. It's also the same distribution from which the test statistics come from. And so in a claim about a single population proportion, the test statistic was a z-score. So it came from a standard normal distribution. And so our p-value is going to be an area underneath a standard normal bell curve. And exactly how we calculate that p-value all depends on the form of the alternative hypothesis. And so if we have the form p greater than a number, then the p-value is the area underneath the standard normal bell curve to the right of z. And this type of test is generically called a right-tailed test. If the alternative hypothesis is that p is less than a number, then the p-value is the area underneath the standard normal bell curve to the left of z, the test statistic. This is what we call a left-tailed test. Now, if we have an alternative hypothesis p is not equal to some number, then the p-value is twice the area to the left or right of z, whichever of those areas is smaller. And this type of test is called a two-tailed test. Now, we use the p-value to come to the technical conclusion using these criteria. Number one, we reject the null hypothesis if the p-value is less than alpha, and we do not reject the null hypothesis if the p-value is greater than alpha. So there's no critical region here. All we have to do is compare that p-value to alpha. If the p-value is less than alpha, then we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. Now, this figure here illustrates how to calculate the test statistic, or excuse me, how to calculate the p-value. So in a right-tailed test, we have an alternative hypothesis of p greater than some number. And so here's our test statistic. Here's our standard normal bell curve. And so the p-value is the area underneath that bell curve to the right of z. And so we see why this is called a right-tailed test. In a left-tailed test, we have alternative hypothesis p less than some number. Here's our test statistic. The p-value is the area to the left of that. Now, in a two-tailed test, things are a little bit more complicated. In a two-tailed test, our test statistic could be negative or it could be positive. If we get a negative test statistic, then the area to the left is smaller than the area to the right. So we find that area to the left, take it times 2, and we get our p-value. If our test statistic is positive, then the area to the right is less than the area to the left. So we find that area to the right, take it times 2, and we get our p-value. Okay. So going back to our example, our alternative hypothesis was the statement that p is greater than 1/2. And so this is a right-tailed test. And so from our figure, we see that our p-value is going to be the area underneath the bell curve to the right of the test statistic. Our test statistic was 2.36. And so if we go to table C1, our z-score table, and look up z equal 2.36, we're going to find that the area to the left is 0.9909. That's the area of the unshaded region down here. And so to find the area of the shaded region, we subtract that from 1, and we get 0.0091. So that number is our p-value. Now, to come to our technical conclusion, we simply compare that p-value to our significance level alpha. Again, our significance level is 0.05. In this case, the p-value is less than alpha. And so the technical conclusion would be to reject the null hypothesis. Now, that's the exact same technical conclusion that we reached using critical regions. And then from this technical conclusion, we would come to the same final conclusion as we did using critical regions. So again, the p-value method is just an alternative way of coming to the technical conclusion. And in either method, we should come to the exact same technical conclusion and the exact same final conclusion.